Okay, think about the ocean for a sec. You've got the big waves, obviously, but also those, constant little ripples on the surface.
Mm-hmm.
Well, space-time, the actual fabric of the universe, kind of has something similar. Gravitational waves.
Right, these incredibly faint ripples passing through, well, everything, all the time.
Exactly. And for this deep dive, we're looking at a really innovative new idea for detecting them. It comes from Jeremy Darling over at the University of Colorado Boulder.
Yeah, and what's really interesting is how it differs from the established way we've tried to sense these things directly.
You mean using pulsars?
Exactly. Pulsar timing arrays are great, but they mostly pick up waves moving, towards us or away from us along our line of sight.
Because they mess with the timing of those pulsar signals reaching us.
Precisely. These pulsars are like amazing cosmic clocks, but Darling's work. The exciting part is it might let us see the full picture, the three-dimensional nature of these waves.
Ah, okay. So, our goal today is to really dig into this new technique. What could it tell us about the universe? Stuff like the basics of gravity, maybe even how galaxies evolve.
Definitely. And it's timely, too, because we just had that big news from Nanograv, right? Detecting the background hum using pulsars.
Right. So we know these waves are out there, but imagine seeing them not just as this push-pull, but like from all angles.
That's the potential here. Darling's idea is maybe we can see this by watching quasars, these super bright, distant objects.
See if they appear to wiggle as space-time gets stretched and squeezed around them.
That's the essence of it, yeah. Okay, so let's unpack how that might work.
Right.
So Darling laid this out in the Astrophysical Journal letters. He's looking at quasars to try and spot these 3D effects of gravitational waves.
And where are these waves even coming from?
We think the main source, especially for the low-frequency ones he's interested in, are these colossal collisions, supermassive black holes merging.
Wow, like galaxy-center black holes crashing together.
Exactly. Throughout cosmic history, these send out ripples, but they're very long wavelength ripples. Low frequency, meaning they take years, maybe even decades, just to pass by us.
Years or decades. That really gives you a sense of scale.
Yeah.
Okay, so you mentioned the pulsar timing arrays, Nanograv, and others. How is Darling's method fundamentally different?
Right. So pulsar timing, as we said, measures tiny changes in when the pulses arrive. A gravitational wave passes through, stretches or squeezes the space between us and the pulsar.
And the pulse arrives a tiny bit early or late, that push-pull thing.
Exactly. Darling's approach is trying to catch the other effects, the sideways motion, the up and down distortion of space-time.
Got it. So not just squashing and stretching along our line of sight, but maybe a kind of shearing across our line of sight.
Precisely, a transverse effect. And the keys to seeing this, potentially, are quasars.
Okay, remind us what are quasars again.
They're basically incredibly luminous cores of very distant galaxies, powered by supermassive black holes actively feeding on surrounding material, millions, often billions of light years away.
And they're super bright, which helps, I guess.
It does. And their distance, maybe counterintuitively, is also key.
Okay, so we're looking at these incredibly distant bright spots.
Mm-hmm.
How does the gravitational waves makes them look like they're moving? They're not actually physically moving across the sky, are they?
No, they're not. This is where a field called astrometry comes in.
Astrometry. Measuring positions.
Exactly. The precise measurement of positions and movements of things in the sky. Now, imagine light traveling from a quasar, billions of light years away.
Okay.
As a gravitational wave passes through the space that light is traveling through, it can slightly bend the path of that light.
Ah, like lensing, but caused by the wave itself.
Sort of, yeah. Think of it like a curveball. The wave subtly changes the light's trajectory on its way to us.
So even though the quasar is sitting still way out there, the light arriving here seems to come from a slightly different direction because of the wave passing through, making it look like it wiggled.
That's the core idea, simple in concept, but the effect is expected to be absolutely tiny.
How tiny are we talking?
Get this. The precision needed is something like 10 times better than trying to watch a fingernail grow on the moon seen from Earth.
Wow. Okay. That's mind-bogglingly small.
It really is a huge challenge.
Yeah, and it's not just that tiny apparent wiggle we need to find, is it? Because, well, we're moving too. a lot.
Oh, absolutely. That's another massive hurdle. Earth is whooping around the sun at, what, 67,000 miles per hour?
Something like that, yeah.
And the sun itself is moving around the galaxy center at maybe 850,000 miles per hour. All that motion has to be perfectly accounted for and subtracted out to even hope to see this tiny quasar wiggle.
So how on earth does Darling even attempt that?
Yeah.
How do you untangle our emotion from this potential signal?
He's leveraging this incredible data set from the European Space Agency's Gaia satellite.
Gaia, the big star mapping mission.
Exactly. Launched back in 2013. It's been measuring the positions of, like, over 1 billion stars with insane precision. And crucially for this, it's also observed over 1 million quasars.
Okay, so a massive, precise catalog of quasar positions over time.
Right. Gaia gives us positions over about the first 3 years of its operation in the current data releases.
And what does Darling do with that data? What's the specific method?
His approach is pretty clever. He essentially looks at the quasars in pairs.
Pairs? Why pairs?
Because if a gravitational wave is passing through, it should cause nearby quasars in the sky to appear to move in a correlated way. So he meticulously measures the relative changes in position between pairs of quasars over the time Gaia observed them.
Looking for a specific pattern of coordinated wiggling across the sky.
That's the idea, a pattern consistent with the 3D stretching and squeezing from a gravitational wave background.
Okay. Has he found it? Is this the discovery of the wiggle?
Well, not yet. His analysis, using that initial Gaia data, puts some limits on things and shows the method is potentially sensitive enough, which is important,
But no conclusive wiggle detected so far.
Right. The signal, if it's there, is still sort of buried in the noise of the measurements at this point. It's not statistically significant proof yet.
Okay. But let's say this works out eventually. If they do detect this, what's the big deal? Why is it so important?
Oh, the potential payoff is huge. I mean, first, understanding gravitational waves themselves much better.
Like their 3D structure.
Exactly. Seeing these other polarizations, these different orientations of the waves, it could tell us fundamental things about gravity. Maybe even test if Einstein's theory is the whole story, or if there are, other aspects to gravity.
Testing general relativity itself. Wow.
Potentially. And second, remember, these waves are mainly from supermassive black hole mergers.
Right.
Understanding those events better through their gravitational wave signatures could give us huge insights into how galaxies actually form and evolve over cosmic time, since those mergers are thought to be really key processes.
That makes sense. So it connects the smallest scales of space-time ripples to the largest scales of galaxy evolution.
Mm-hmm.
And I heard there's more data coming.
Yes, that's the really hopeful part. Gaia is scheduled for another big data release, DR4, expected around 2026.
And that will include more observation time.
That's right. It should add about another 5.5 years of observations on top of what Darling used, a much longer time baseline.
Which could make these incredibly faint signals easier to pull out of the noise.
That's the hope. If there's a consistent, tiny wiggle pattern happening over that longer period, it becomes much harder to dismiss as just random measurement errors. It might just provide the breakthrough needed.
So this whole idea, observing the 3D effects of gravitational waves by watching distant quasars wiggle, it's still very much a live possibility. Really ingenious work.
It really is, and it makes you think, doesn't it? The universe isn't just static up there. It's this dynamic fabric, constantly being subtly warped and distorted by these waves passing through.
Yeah. Imagine if we could actually perceive those shifts directly in all 3 dimensions. How would that change how we see things like, those huge black hole collisions or the early universe?
That's some mind-bending thought for sure.
Yeah.
It definitely changes your perspective.
Absolutely. So something to keep an eye on then. Maybe mark your calendars for 2026. See what that next Gaia data drop brings.
Could be some really exciting news about this gravitational wave background.
Because even these tiny, almost imperceptible cosmic wiggles, they might just unlock some incredibly deep secrets about how the universe works.